Today is our second class of GATE Aerospace TEMS Academy for Aerodynamics. And in our last class, we have presented, we have covered topics like lifting line theory, then thin aerofoil theory, and we have solved some problems regarding thin aerofoil theory and also lifting line theory and downwash, wash in, wash out, geometric twist, aerodynamic twist. These are topics we have covered in our last session. And in our today's session, we will be seeing forward swept wing, lift distribution on a finite wing, compressibility, aspects of supersonic flow, thermodynamic relations, shock wave, and normal shock. So first, in our last class itself, we have a small doubt in forward swept wing. Why forward swept wing is chosen for military aircrafts, and what is the advantage over it towards the aft swept wing? So in aft swept wing, the vortices will be formed at the wing tip, but in forward swept wing, you can see this is the arrow mark. This arrow mark shows the flow which comes inside the flow inside the aircraft into the aircraft while in flight. So in aft swept wing, that means backward swept wing, it is clear that the air is coming to the from the root 2. It leaves the airplane wings through the tip. So because of this, what will happen means the tip will get some wingtip vortices. But in forward swept wing, that main advantage is the air which enters the wing from the tip and it leaves out from the root. So because of this, the root only will stall first, but the tip, it won't stall first. There's it reduces the drag because of the tip vortices. So this is the main advantage of forward swept wing, and also the CG is also it is placed backward. So the main advantages are it reduces tip stall, and also but one of the disadvantage in in forward swept wing is the yaw instability. That is during it produces adverse yaw in a reverse manner. That's one of the disadvantage of forward swept wing. And also another one major advantage is the maneuverability is also increased, and also the coefficient of lift is also increased for forward swept wing. That's why forward swept wing is preferred. So I think the doubt which was in last session is cleared from this concept. So before rendering, we will be having a small glance about our last 10 questions. So in our last class, we had a mock test for the previous session. So the first question is, by Kelvin's circulation theorem, around the aerofoil, the vorticity in the starting vortex is matched by the vorticity of. The answer is bound vortex, because around the aerofoil the vortex vorticity found or vortex formed is bound vortex only. So the answer is bound vortex. Then second question, Kuta condition is applied to aerofoils having, you already know, in order to satisfy Kuta condition, the vortex time that the trailing edge should be equal to 0. So the stagnation, and also the stagnation point should be at the trailing edge. So without a trailing edge, there won't be any, the Kuta condition cannot be satisfied. So therefore, in order to satisfy Kuta condition, the airfoil should have a sharp trailing edge. So the answer is A, sharp trailing edge. The third question, lift curve slope. Students, anyone please respond whether I am audible to everyone and my screen is visible to everyone.
Yes, sir.
Okay, fine. So third question is lift curve slope value of aerofoil having cusped trailing angle. So in our last session itself, we discussed that the lift curve slope value, it won't change no matter the what the aerofoil is. Maybe it is a circular aerofoil, sorry, a symmetrical aerofoil, or it is a supercritical aerofoil, or whatever aerofoil may be. Maybe it is a cambered aerofoil. The lift curve slope value, it won't change. The value of lift curve slope is 2 pi, and notation for lift curve slope is A. So here the answer is that we have 4 answers. One is 2 pi, 2a, 2 pi a, 2 theta. We know the answer is 2 pi. Because the lift curve slope, it won't change. For whatever aerofoils, the slope values remain same. So our next question is major advantages of forward swept wing. What are the advantages? I already discussed now itself, and in the last session also we discussed it. So forward swept wing, the main advantages are it maneuverability is increased even at a high angle of attack, and also the lift coefficient is also increased, and we know that for forward swept wing, that wing tip vortices is also reduced. So therefore, all the 3 answers are correct. Therefore, I mentioned the answer is D, all the above. So it have the properties like reduced wing tip vortices, maximum lift coefficient, and also increased maneuverability at high angle of attack. These 3 things contribute to forward swept wing. Then, so the forward swept wing has one of the instability. It has an instability. The instability created by the forward swept wing is, from these answers, we have roll instability, yaw instability, pitch instability, and none of the above. But the answer is yaw instability, because forward swept wing produces adverse yaw effect in a reverse manner. So the instability created by adverse yaw is yaw instability. Therefore, forward swept wing, the instability dominated is yaw instability. So the answer is B. Then next question, lifting line theory. You know, the lifting line theory is applicable for lifting line theory is derived by Prandtl, and we know that it is it is applicable for 3D wing. 3D wing means 3-dimensional wing, so a complete wing. So complete wing, we will call it as a finite wing, and infinite wing means it is an we will call the infinite wing as a aerofoil. This Prandtl lifting line theory is not applicable for aerofoils and infinite wing. It is applicable for only finite wing. Therefore, the answer is C. The lifting line theory is applicable only for finite wing. So next one, if the vortex flow is anti-clockwise, then the strength of vortex is, if the vortex flow is anti-clockwise means the strength of vortex will be in negative manner. If the vortex flow is in clockwise, then it will be in positive manner. So the answer is negative. Then 8th one, the CP location of cambered aerofoil answers are varies with angle of attack, remains same as aerodynamic center, none of the above. For symmetrical aerofoil, the CP and aerodynamic center are in a same location. But in cambered aerofoil, we last in the last session itself, we have seen that in thin aerofoil theory, for cambered aerofoil, we find that XCP value is location of the CP. So the why we are finding the CP value is because during a high angle of attack, the lift increases, and because of the lift change in lift, there will be a change in the location of the CP value, center of pressure value. So the center of pressure location for cambered aerofoil changes with angle of attack. Therefore, the answer is it varies with angle of attack. It won't remain same, and it will not be same as the aerodynamic center. Only for symmetrical aerofoil, the CP value it remains same as the aerodynamic center. The next one, in a finite wing, the maximum lift coefficient is generated at which section? One is tip, mid, root, all the above. So in a finite wing, the maximum lift coefficient, we know the maximum lift coefficient will be generated at the root only, root section of the aerofoil. It won't be created at the tip section. Therefore, the answer is C, root section. The next thing, according to Kelvin circulation theorem, the rate of change of circulation around a closed curve is the rate of change of circulation around a closed curve is answer is D, 0, because we know that d gamma by dt equals equal to 0. That is Kelvin circulation theorem. Therefore, the rate of change of circulation around a closed curve is equal to 0. Then the part B questions, the 2 more questions that we need to solve. The first question we have already solved in our in the last session itself. The rate of change of moment coefficient with respect to angle of attack dCm divided by d alpha at a half chord point of a thin aerofoil as per approximation from the thin aerofoil theory. The answer is pi by 2 radians raised to -1. And also here this symmetrical aerofoil, same we have solved it. That is, consider a symmetrical aerofoil at an angle of attack of 4 degrees using thin aerofoil theory. The magnitude of moment coefficient about the leading edge is pi square by 90. I think all these problems you have, it is okay for you. Whether you guys able to solve these questions? Anyone please reply. See here, the 6th question. The zero lift angle of attack of thin aerofoil theory at 4 degree angle of attack is, the answer will be 0, because for thin symmetrical aerofoil there won't be any zero lift angle of attack. Only for cambered aerofoil we will be having zero lift angle of attack. Therefore, the answer will be 0. Then see here, the induced velocity of infinite length is pi by 2 pi h, gamma by 2 pi h. But for semi-infinite length, it is gamma by 4 pi h. And one more thing here, see, the Helmholtz theorem is applicable for inviscid compressible flow, inviscid incompressible flow, inviscid irrotational flow, and none of the above. It is applicable only for inviscid incompressible flow. Other all things, see this consider a thin symmetrical aerofoil at 1.5 degree angle of attack. From the results of thin aerofoil theory, calculate the moment coefficient about the leading edge. So we have a formula for a moment coefficient at the leading edge. By using that formula, just with the first we need to change the angle of attack in degrees to radian. After that, by using the formula, directly substitute and find the answer. The answer is 0.041. Here, same way, first we need to change the degree to angle of attack degree to radian. After that, apply that lift coefficient 2 pi alpha. So alpha is 1.5 into pi by 180. By applying that, we will get the answer. Here also the same only. Okay, fine. So I think the questions in the last sessions are mock test is okay for you. Now we'll be seeing our today's presentation. So once again, I am repeating the forward swept wing is an aircraft wing configuration in which the quarter chord line of the wing has a forward sweep. Typically, the leading edge also sweep forward. So the leading edge is swept forward, and the major advantage is it reduces tip stall, and also it increases the maneuverability and also the maximum lift coefficient of the wing. And the problem which encounters in forward swept wing is yaw instability. So next thing is, in the last session we have covered the Prandtl lifting line theory. So for a finite wing, now we are considering the elliptical lift distribution. So there will be small changes in lift distribution for normal wing and for elliptical the elliptical lift distribution. So here the circulation distribution for elliptical wing is given by gamma of circulation gamma of y equal to gamma naught. Gamma naught means the circulation of the origin. Here in this point the circulation is gamma naught, and square root of 1 minus 2 y by b the whole square. This is the standard formula for circulation of elliptical wing. Here the circulation value they have calculated and put the gamma of y equal to gamma naught into square root of 1 minus 2y by b the whole square. So here the circulation is gamma naught at the origin, and we know after finding the circulation we can easily find the lift coefficient, that is L equal to rho v gamma. So from that we can if we have the value of this gamma, we can easily find, and also by substituting the value of rho and v infinity, we can easily find the value of lift. Then we all know in Prandtl lifting line theory, we found that the circulation of at the tips are at the wing tips is equal to 0. It changes along the chord. Along the chord, lift distribution changes that we can see in this diagram. So at the tips, the lift distribution is 0 because the circulation is 0 at the wing tip, and over the chord it increases. It increases. So yeah, along the chord it increases. So here I mentioned this gamma of b by 2 and gamma of minus b by 2 equal to 0. So it's this gamma of b by 2 is the sessions for here this end and this end. So this is minus b by 2, and the opposite end is b by 2. So therefore both the wing tips, the circulation is equal to 0. Then we all know that from the Prandtl lifting line theory, the downwash formula is W of y naught equal to minus 1 by 4 pi integral of minus b by 2 to b by 2 d gamma by dy of dy divided by y naught minus y. So here, in order to find the downwash, we need to know the value of d gamma by dy. So what I am doing is differentiating the value of gamma. Here we have the value of gamma in terms of y only. So differentiate with respect to y. So d gamma by dy equal to minus 4 gamma naught divided by b square into y square divided by 1 minus 4 y square divided by b square the whole power 1 by 2. So I am substituting this d gamma by dy value in w of y naught. So downwash equal to gamma naught divided by, here we have 4, and here also we have 4. 4 get cancelled, and remaining thing is pi. Here we have pi, and substituting this value, we will be getting gamma naught divided by pi into b square, then integral of minus b to b by 2 y divided by 1 minus 4 y square divided by b square whole power 1 by 2 into this value y naught minus y into dy. So here we have two unknowns. That is, one is the y, and another one is three unknowns: y naught and dy. So already in thin aerofoil theory also we have seen this thing. That is, we need to transform this thing. That is because of from the Kutta-Jakovsky transformation itself, we will be seeing that we can transform on a circle into an aerofoil, a circle into a flat plate, and a flat plate into an aerofoil. Based upon that transformations, we are applying y equal to d by 2 cos theta, and also in differentiation of this y. Thus dy is equal to minus b by 2 cos theta will be become b by 2 cos theta will become minus sin theta into d theta. So applying this, we will be getting w of theta naught equal to minus gamma naught divided by 2 pi b integral of pi to 0 cos theta divided by cos theta dot minus cos theta into d theta. So by changing the integral, like from 0 to pi, we will be getting cos theta divided by this cos theta minus cos theta naught into d theta. So in the last session,
excuse me, sir.
Yes.
Sir, can you please tell me the value of theta naught again, sir?
See, theta naught, there is no, there is not theta naught. Theta 1, we will be calling it as theta 1. That for your understanding only, they are putting a theta naught. Okay. So we have that specific formula that we have seen in our last session itself. Integral of cos theta divided by cos theta naught minus cos theta minus theta naught into d theta equal to pi sin theta divided by sin n theta. That I have shown in your last class. I think you know that. So here also, see, so in this, here also we will be having for this for this thing, integral of 0 to pi cos theta minus divided by cos theta minus cos theta theta naught into d theta. We will be having the formula like pi into sin theta divided by sin. So we will be getting pi for this session, for this thing. So applying here, pi get cancelled. The remaining value will be minus gamma naught divided by 2 into b. So for a elliptical lift distribution, if we want to find the downwash, the formula is minus gamma naught divided by 2 beta. So if you know the span of the wing and also the circulation at the origin value, we will be we can easily calculate the downwash value. So if we know the downwash, we, in the last class itself, from the geometrical geometry of aerofoil, we know that the induced angle of attack is equal to minus w by v infinity. The W is the downwash, and V infinity is the free stream velocity. So applying this, downwash equal to gamma naught divided by 2. Here minus get cancelled. Then the remaining thing is gamma naught divided by 2B into V infinity. So this is the value for induced angle of attack. So suppose you're getting a problem like this, find the induced angle of attack for 50 meter span, and the circulation value they have given on circulation, any circulation value means, then you need to calculate the calculate the induced angle of attack based upon this formula. Okay. Okay, fine. Then for an elliptical lift distribution, the induced angle of attack is also constant along the span. Note these things. For an elliptical lift distribution, the induced angle of attack will be constant along the span. No matter the span, it remains constant. We all know lift is equal to rho infinity v infinity gamma naught integral of minus b by 2 to b by 2 1 minus 4 y square divided by b square whole power 1 by 2 into dy. By applying the transformation, we will be getting like this. So applying the transformation here, that is y equal to b by 2 cos theta. Therefore 4 into 4 b square divided by 4 into cos square theta. It will coming like this 1 minus, so this time I'm expanding this term, so 1 minus 4 into b square divided by 2 square is 4, so again 4 into cos square theta divided by b square. So 4 get cancelled, b square get cancelled, so remaining is cos square 1 minus cos square theta. We know 1 minus cos square theta is equal to sine square theta. So from that, here you know the remaining terms are rho infinity v infinity gamma naught into integral of minus b by 2 to b by 2 sine square theta, d theta. Then so applying this values and all, we will be getting rho equal to lift equal to rho infinity v infinity gamma naught b square by 4 into pi. And here we have another one transformation also, because for sine square theta d theta, we have a formula like 1 minus cos 2 theta divided by 2. See, for thin aerofoil theory, Kutta-Jakovsky transformation, and also for Prandtl lifting line theory, these all things we will be having some trigonometric relations. We need to know this trigonometric formulas and all. After if you know that formulas, we can easily substitute the formulas and we can solve the things. Because while solving thin aerofoil theory, it is the most important thing, because there will be getting integral of sine square theta d theta formula, and also integral of sine cube theta d theta formula, integral of sine theta d theta formula. Same way, integral of cos square theta d theta formula, integral of cos theta d theta formula. So remember all these formula, or just study that formula, or remember those formulas. Okay, then it will be helpful for you. Okay, so after substituting this and solving this, we will be getting the value like rho infinity v infinity gamma naught b by 4 into pi. So from this thing, we can calculate the value for gamma naught. So if you want to calculate the value for gamma naught, we need, and by knowing the lift value, we can easily calculate the gamma naught value. The circulation at the origin is equal to 4L divided by rho infinity V infinity B pi. So in some problems, I've seen that they are asking they have given the value for lift like 80 kilonewton, and the span is 10 meter, and find the circulation at the origin and circulation at the or they will ask the circulation, find the circulation at the tips. So we all know for elliptical wing and also for rectangular wing and all, for elliptical wing lift distribution and all, the circulation at the tip is equal to 0, and also the lift distribution is also 0 at the tips, but at the root the value changes. For the root they will ask circulation, they won't ask like circulation at the origin, they will ask like circulation at the root. So for finding the circulation at the root, by applying this formula we can easily find the lift. So suppose they think that L equal to 80 kilonewton, and also the span B equal to 10 meter, and rho infinity 1.2, rho is 1.2, velocity is 100. So if you are given data like this, whether you can find the value at root? Anyone? Anyone, please? Hello, students. I'm audible?
Yes, sir.
Yes.
I'm getting it to be 84.88, sir.
84.88 meter square per second. Okay.
Second.
There is a unit for this circulation. So now you all know how to calculate this circulation value based upon this formula. Or suppose they have given that CL value, and CL value means by using this next formula, this gamma naught equal to 2 into V infinity S CL divided by B pi, because we know L equal to half rho infinity V infinity square S into CL. By applying this formula, we can easily get gamma naught equal to 2 in V infinity S, because V infinity square here the denominator we have on V infinity, that get cancelled, and rho infinity get cancelled, then 2 here on 4 it get cancelled, and they will be getting 2 V infinity S CL divided by B into pi. So now see here, induced angle of attack, the formula is alpha I equal to gamma naught divided by 2B into V infinity. So we found the gamma naught value here. So substituting the gamma naught value in induced angle of attack formula, we will be getting 2B infinity S CL divided by B pi into 1 divided by, that is alpha I value, gamma naught divided by 2B V infinity by after substitution. This is the gamma naught value, and remaining things here 2B into V infinity. So 2 can cancel, B square, then V infinity get cancelled. So remaining things will be alpha I is equal to S into CL divided by pi into B square. So alpha is equal to CL divided by pi into AR. AR means aspect ratio. We know the aspect ratio is equal to B square by S. Aspect ratio is equal to B square by S. By substituting here, we will be getting alpha is equal to CL divided by pi into AR. So from here, if the coefficient of lift increases, automatically the induced angle of attack is also will also increase. Then if aspect ratio increases, what will happen? What will happen when aspect ratio increases?
Induced lift decreases, sir.
Yes, induced angle of attack will decrease. Okay. So here alpha equal to CL divided by pi AR, and also now we will be finding the induced drag coefficient. So in the induced drag coefficient is also same. The formula is CDI equal to 2 pi 2 alpha I divided by V infinity S integral of minus B by 2 to B by 2 gamma of Y dy. So see, sometimes they will be asking questions like this. See in aerodynamics and all, they will be asking questions from some note values. See, in a book itself, they will be given some sentence note that for infinity, if m1 is infinity, then the value will be something. These kind of things you should focus on, because they will be asking questions relevant to that type only. Okay. So for after substituting the value for gamma of y and dy, we will be getting the induced drag coefficient is equal to pi b divided by 2 into v infinity s into CL divided by pi AR 2 V infinity S CL divided by B pi. So 2 get cancelled. CL into CL square it will come. Then V infinity get cancelled. B pi it will cancel. And S cancelled. Remaining terms will be CDA equal to CL square divided by pi AR. So for induced drag coefficient is equal to CL square divided by pi AR. That means, but we know that CDI induced drag coefficient value, that is equal to CL square divided by pi into E into AR. But here we have seen that CDI equal to CL square divided by pi AR. Anyone know what's the difference between these two things?
Sir, E is Oswald efficiency factor. It's used to calculate the drag over the entire wing. Incorporate the drag over the entire wing.
Okay, fine. But here one difference is there. What is the difference between these two formulas? Just you can see from the formula itself, there is a small difference.
Sir, in the denominator, E is the Oswald efficiency factor, which is used to incorporate the drag over the entire wing.
Okay. Here also we are calculating the for entire wing only. Elliptical distribution for entire wing only.
So for elliptical wing, E value is 1, sir?
Yes, the elliptical wing, E value is 1. For other wings, the E value differs. So based upon the E value only, we will be calculating the induced drag coefficient. But other thing also there, because induced drag coefficient, it is directly proportional to the square of lift coefficient. So the value, and also inversely proportional to the aspect ratio. But apart from that, we have another one value also, that is asphalt efficiency, that is E. That asphalt efficiency is E will be for elliptical wing, the E will be 1. So because of that only, the formula becomes CDA equal to CL square divided by pi AR. This is one of the questions from gate questions only. For what is the value of induced drag coefficient for elliptical wing? That we need to apply like E equal to 1, and after that they will they have given some formulas, values for CL and aspect ratio. After that, we need to find the by substituting the values, we need to find the induced drag coefficient. Okay. So suppose the aspect ratio is high, what will happen? For induced drag coefficient, if the aspect ratio is high, what will happen? Automatically
CD will be decreased, sir.
Decreasing. So if the aspect ratio is less, the CD will be increasing. So that's why we are choosing high aspect ratio wing in order to reduce the induced drag coefficient. Okay, then CL is equal to another one term for lift coefficient. CL is equal to this formulas and all already we have seen in the airfoil geometry in the last session. That is CL is equal to A naught into pi alpha efficient effective minus alpha L equal to 0. So the lift for per unit span is equal to L of y equal to Q infinity. Q infinity we know that the dynamic pressure half rho infinity V infinity square into C into CL. That is not C, S into C for per unit span. Therefore it becomes S area will be 1 into C. Therefore Q infinity C into CL. So C equal to C of y, and that is equal to L of y divided by Q infinity into CL. So from this formula, we know that the chord must vary elliptically along the span. The chord value changes. Okay. Then so I was told that the asphalt efficiency factor E for this elliptical span now. So E that is equal to 1 plus del whole power minus 1. This is the value. So induced drag coefficient that is equal to CL square divided by pi AR into 1 plus del. So del is the induced drag factor. So in that induced drag factor for elliptical wing, it is equal to 0. Therefore, the E will become 1. So the formula become CDA equal to CL square divided by pi into AR. Otherwise, the formula will be CDA equal to CL square divided by pi E into AR. So next is the aspect ratio. We all know the aspect ratio is equal to B square by S. Square of span divided by area of the wing. Okay. So we know the this is the relation for the values relating the A naught and A. So A naught and A are related as DCL divided by D of pi minus pi alpha minus alpha I equal to A naught. And so here for elliptical, that is for elliptical planform and normal finite wing planform, the finite for elliptical planform DCL divided by D alpha. No need of this all things here. We will be focusing on this one formula, this two formulas only. So for elliptical planform, this lift curve slope DCL by D alpha equal to, that is A equal to A naught divided by 1 plus A naught divided by pi into AR. And for a finite general planform wing, A equal to A naught divided by 1 plus A naught into A naught divided by pi AR into 1 plus tau. So that is for aspect ratios, and we will be seeing some problems here now. So our first problem is the span-wise distribution of circulation over a finite wing of span B equal to 10 meter. So the span we have they have given the span as 10 meter, and they have given a gamma y circulation formula. Circulation equal to gamma naught into 1 minus square root of 1 minus 2y square divided by b, 2y the whole square divided by b. If gamma naught equal to 20 meter per second. Okay, sorry. It's not meter square, I think so. And the free stream density are 1.2 kilogram per meter cube and 100 meter per second, the velocity. The total lift is dash kilonewton. That we need to find the total lift, that is L. L we need to find. We know the L equal to rho infinity rho V gamma. So first we need to substitute that. So whether you can calculate this problem. You can solve this problem. So just I will give the hint. Please solve the problem. L equal to rho V gamma. So gamma we know, gamma equal to gamma of gamma naught into square root of 1 minus 2y by b the whole square. So gamma naught they have given 20 into 1 minus 2y divided by b the whole square. Can you able to solve this? Anyone? Please try to solve this problem.
Excuse me, sir.
Yes.
So in that formula, the B value has been given, sir, but Y value?
Yes. Okay. Y value we know that y equal to b by 2 cos theta.
Oh, okay. Understood. Okay, sir. Excuse me, sir.
Yes.
So I'm getting something around 2400 sin theta.
Value for lift.
Yes, sir.
What answer?
2400 sin theta.
No, it won't come like that. And one more thing. See, we can't solve the sum with that y equal to b cos theta, b by 2 cos theta, and we need to substitute if you are substituting that y, we need to substitute that dy also, dy value also, because first we need to integrate this differentiate this gamma with respect to, we have seen the derivation now. First the
Yes, sir.
formula will be first we need to substitute like this, d gamma divided by dy like and like that. So for your simplicity will be showing these things. See here, we need to use this formula. L equal to rho infinity v infinity gamma naught integral of minus b by 2 to b by 2 1 minus 4 y square divided by b square the whole power 1 by 2 into dy. So after that, using transformation, I told that after transformation, the formula is reduced to rho infinity v infinity gamma naught b by 4 into 5. Suppose
Okay.
you don't know
Okay, sir.
that value only, we need to use that transformation, because if you want to apply the transformation, we need to do two things. First, y equal to b by 2 cos theta, we need to substitute here. And after that, we know here one more term is there, that is dy. The dy term, we need to apply the dy term also. So for dy term, we need to differentiate this y. So differentiating dy equal to b by 2 cos theta, it will become minus sin theta. Therefore, minus b by 2 sin theta. So substitute that also. And 1 minus cos square theta, it will reduce to sin square theta. And the sin square theta, it will be changed after substituting the value. Then one more thing. See here, we have minus b by 2 to b by 2. What we take here, this from here, minus b by 2 to b by 2. So this minus b by 2 value, we will be taking as 0 to pi value. It will become 0 to pi. Therefore, the limit will be 0 to pi sin square theta d theta. After applying all these things or substituting all those values, we will be getting the formula like rho infinity v infinity gamma naught b by 4 into pi. Okay. So in this formula, you need to substitute the values. So we know rho infinity is rho infinity value at 1.2. Okay. So here rho infinity value 1.2, then v infinity value that is 100 meter per second, then gamma naught value 20 meter square by second, and finally what b value here 10 meter into 10 divided by 4 into pi square, sorry, into pi. Now solve this sum and tell the answer. I will show you the formula. Just note this formula.
Excuse me, sir.
Yes.
I'm getting it as 1 second. 18.84 kilonewton.
Yes. Answer is correct. Whether others got this answer? Others, please respond.
Yes, sir.
Yes, all of them got the same results. So here also see, for rho, the unit is kilogram per meter cube. Then for velocity, meter per second. Here meter square per second. Then for span, it is meter. Here a meter cube. Here we have meter, meter square, meter. Therefore meter per m power 4. Here in the denominator, we will be having meter cube. So we will cancelling. We'll be getting here a kilogram divided by meter second. So meter second square. So the unit will be kilogram meter per second square. So 1 kilogram per meter kilogram meter per second square equal to this 1 kg meter per second square equal to 0.001 kilonewton. Please note this also, that you all know that you can you know that 1 kilogram meter per second square is equal to 0.001 kilonewton. So from this, the answer is answer for this total lift is, by substituting all these things, we will be getting the lift value is L equal to 18.84 kilonewton. So all of them got this value. Everyone, hello.
Yeah, got
So
it, sir.
everyone, okay, fine. So we will be moving on to our next problem. So this problem is from this thin airfoil theory only, for simplification, so for some small understanding, whether you have remembered that last class, that for that purpose only I have put this problem. So same thing, angle 10 degree, assuming a thin airfoil theory, the magnitude of pitching moment coefficient about leading edges. Do you know how to calculate this? Students, please calculate this, solve the sum and tell the answer. So we have this angle of attack as 10 degree, and we need to find the pitching moment coefficient at leading edge. Please calculate this.
Sir, is it 15.70?
No.
Okay.
How you calculated?
So that Cm is equal to Cl by 4 formula. And Cl is equal to minus 2 pi alpha.
CL equal to minus 2.4. Yes, once again. Yes, yes, Cm leading edge is equal to minus pi alpha divided by 2. Have you used that formula? Pitching moment coefficient.
No, sir. I used the different formula.
Which formula used?
Cl by 4, sir. Cm is equal to Cl by 4.
Yes, but CL value, do you know the CL value?
Cl value
Somehow
is
the same answer will be, you'll be getting the same answer only, na? Yes, sir. Somehow you will be getting the same answer. Whether you converted that alpha value?
No, sir. Sorry.
Yes.
That only
Yes. First
degrees
thing
value.
you need to convert that degree value, because remember one thing, for in thin airfoil theory, yeah, that everything will be in radians. Okay, that is
Yes, sir.
not in degrees. So first you have to convert the degree into radian. After that only we need to solve this.
Excuse me, sir.
Yes.
Sir, is it minus 0.02739?
Minus 0 point?
0.02739.
No.
No.
Check it once again.
Sir, actually, CMLE is equal to minus pi alpha by 2.
Yes, pi alpha by 2.
Yes, then that is the answer, sir. Actually, 1 degree is equal to 0.01745 radians.
Yes.
After doing this conversion, I'm getting it as minus 0.02739.
Is everyone getting the same answer?
Sir, 0.274.
0.274. Yes, that's the correct answer. what see just put this the degree conversion like this, pi by 180, then it will be easy for you.
So I'm getting just 1 point difference. It's 0.274 he told. I'm getting
Yes,
it as
points. That's why I asked. There is you got 0.0274, but the answer should be between 0.24 to 0.3. If you are getting in the values in between, that means it is okay. So the answer for the moment question is CM leading edge is equal to, it should be between 0.24 to 0.3. See, for your gate and all, the 2 more questions they will be given answers like this only, and you are getting the value like 0.274. That is correct answer. Okay. So for solving the calculations and all, some there will be a minor change now. Like someone get a 0.25, someone get it 0.29 or 27. If you are getting values in between, this means it is okay for us. Okay. So the formula for this CMS leading edges, those who don't know the formula, I will be writing the formula: minus alpha pi divided by 2. So substituting the value of this kind of problems we have solved before also. Substituting the value of pi here, sorry, alpha here, alpha 10 degree, that is 10 into pi by 180, we will be getting the answer like CMS about leading edges equal to 0.274. Okay, fine. Now we will be moving on to our next problem. Okay, fine. So here our next problem, the question is a wing of 15 meter span. So the span is 15 meter with a elliptical wing lift distribution. So here we have studied about elliptic wing lift distribution only. So the problem here also, it is focused on elliptical wing lift distribution. Is generating a lift of 80 kilonewton. So the lift value is equal to 8 kilonewton at a speed of 90 meter per second. So the value of V infinity is equal to 90 meter per second. The density of surrounding air is 1.2 kilogram per meter cube. So density is 1.2 kilogram per meter cube. We need to find the value for induced angle of attack at this condition in degrees. You need to find this induced angle of attack in degrees. So so the given data are V, then L, then V infinity, then rho. So these four things we know. The formula for induced angle of attack is alpha I equal to CL divided by pi into AR. So whether you can able to solve this, or whether I need to solve this problem. So we have L value we know, rho value we know the B value also, V infinity value also we know. Only thing we need to find, we need to substitute this values and we need to find the answer. Whether you can able to find that, students?
So 1.14.
Answer is
1.14.
no. What your answer is
1.14.
Everyone got the same answer, or it should be around 1.3 something. Please check it once again.
One 1.33.
Yes, 1.33. Correct. So I'll be explaining how we will solve this problem. So we know the CL is, L equal to half rho V square S into CL. So we don't know these two values. S also we don't know. This CL also we don't know. But we know the values like lift value, that is 80 equal to half into 1.2, that is a rho value. Then V square value, that is into 90 square. So after so into S into CL. But we know alpha equal to CL divided by pi into AR. That is aspect ratio. That is pi into AR is aspect ratio is equal to B square divided by S. That is S, it will come to numerator. Therefore, CL into S divided by pi into B square. So here also we will be getting the values for S into CL. So substitute the value for S into CL here, and now we know the values for B also. B square we know, that is 15 square. After substituting all those values, we will be getting alpha I equal to 1.33. So the answer should be between 1.292 1.38. So everyone got the answer. If it is between these values, means it is okay. Students?
So it's actually CL into S divided by pi into B square by S, sir?
No, pi into B square.
Okay.
See here, simple. For aspect ratio, the formula is B square by S. I'm substituting in the B square by S here. So B square divided by S. S will be coming in the numerator. But we know the lift value, we have two unknowns, that is S into CL. So straight away I am substituting the value for CL into S here. So it will be getting 160 divided by 1.2 into 90 square. So calculate the value for that and substitute in CL into S value. Okay. After substituting it, we can easily find, because B square also, we know the value for B square also. So by substituting it, we will getting the value for pi. Sorry, we will be getting the value for alpha I. So please solve that. So everyone get the answer? Got the answer?
Yes, sir.
Okay. Other all remaining persons. So in this problem also, one major difficulty is, first of all, we are substituting the value for CL and aspect ratio. That aspect ratio, they only have given the data for V square. They didn't give the value for S, and also CL value is also unknown. So from the lift value, we can easily calculate the CL value, but also here S value is, again the S value is in question mark only, that is unknown value only. So we should substitute the CL and the S value, both value in the induced angle of attack formula. Then only we will be getting the answer. Don't think that we have two unknowns, we can't solve that problem. Okay, this is the small difficulty, because this kind of problems only they will ask. This is the one of the questions from GATE only, GATE problems only. Okay, please respond whether everyone got the answer. Other persons. Students. Shall we move on to the next problem, or I need to stay here?
So we'll move on, sir.
Okay, fine. Okay, then the next one is an untwisted wing of elliptic planform. Same elliptical planform problem only, and aspect ratio 6. So here they have given the aspect ratio consists of thin symmetric airfoil sections. The airfoils are thin symmetrical. The coefficient of lift at a 10-degree angle of attack, assuming inviscid incompressible flow. We need to assume it is an inviscid incompressible flow. The coefficient of lift value at a 10-degree angle of attack. We need to find the lift coefficient value at 10-degree angle of attack. Can you able to solve this? Try to solve this. Okay, I'll be giving one
3.28, sir.
3.28.
No, sir.
No. The value should be in here. See, we have 4 options: pi square by 16, pi square by 12, pi square by 8, pi square by 2. So we need to get the answers from this 4 options only. Okay. So I will be giving one tip for this. From thin aerofoil theory, what is the CL value? So CL equal to 2 pi into alpha, right? this 2 pi is A. But for elliptical planform section, we have this in order to find A, we have one formula, right? So from thin aerofoil theory, the lift coefficient CL equal to 2 pi into alpha. So that's 2 pi is A into alpha. That's A. 2 pi is A. That is lift curve slope. So for elliptical planform section, this A value, we have one formula. The formula is, I'll be writing this formula. That is A is equal to A naught divided by 1 plus A naught divided by pi E AR. Okay. So here we have A naught value. This A naught value is 2 pi. Actually, we should not substitute this 2 pi here, because this 2 pi is for A naught only. So the A naught value will be 2 pi. And we know for elliptical lift distribution, E equal to, we know the E value equal to 1. And in the question itself, they have given that AR equal to 6. That is aspect ratio is equal to 6. So substitute the value for A naught. So A naught will be, that is equal to A naught equal to 2 into pi. So substitute this and find the answer. First find the answer for A naught. Sorry, A value.
So A value is a 4.712.
So you have a substitute that cancel that pi value. Don't cancel the pi value, because the answers should be in pi square now. So keep the pi.
Okay.
And calculate that. I think the same only, but you have substituted multiplied the pi value.
So pi square by 12.
Pi square by 12. The answer is pi square by 12. For A, what is the value for A value? What is the value for A?
3 pi by 2.
Yes, 3. So A equal to 3 pi by 2. Then after that, we need to substitute this A value in CL formula. So the lift coefficient is equal to, there is a CL equal to 3 pi by 2 into 10. Then whether we need to convert that lift into that degrees into radian here. Anyone? Whether we need to convert the degree into radian?
Yes, sir.
Yes, we need to convert the degrees into radian. So for converting that, we need to apply pi by 180. So after substituting this, whether everyone got the answer?
Pi square by 12.
Pi square by 12, everyone got the answer? Guys, everyone got the answer?
Yes, sir.
Yes, sir.
Yes. So the answer is pi square by 12. So if these kind of problems come, whether you can able to solve this, you guys, you're confident in solving this kind of problems, or you're facing any difficulties like this?
So I'm facing one difficulty.
Yes. What is?
So like first of all, to identify the formula itself, I'm taking some time.
Yes, yeah, that it will take some time. You need to by heart that formulas and all. Otherwise, no choice. So why
Yes,
I
sir.
am giving some derivative part means because sometimes you may face some difficulties in remembering the formulas. So in that time, at the time, you can easily solve the derivation, a little bit small derivations and all. Maybe you may know some equations for C alpha equal to W by V infinity. So V infinity, we may get the answers, but for WI, we will be so W the downwash. We should know the formula. So after substituting all those formulas, we can easily derive the formula, and we can get the final value for alpha I, that is induced angle of attack formulas. So likewise, that's why I am focusing on some derivative part also. Okay, because that was most important for you guys. And so one question: uh, what is the value for zero lift angle of attack for a cambered aerofoil? So for a symmetrical aerofoil, there won't be any zero lift angle of attack. But for a cambered aerofoil, what is the values? What is the limit of the value? So maximum values we will be getting for a cambered aerofoil.
Sir, I think it will be -2 to -1 degrees.
Yes, first thing it should be in the minus value. That's the most important thing. So suppose they will be asking questions like whether the zero lift angle of attack, the zero lift angle of attack for cambered aerofoil is negative, zero, positive. You should give the answer like negative, and it should be between -1 to -3. So suppose you are able to solve the problems also, it should be in that value only. The limit should be in up to -3. It should not go beyond that. Okay. Okay, fine. So here the answer is pi square by 12. So another one problem. Consider a wing of elliptical platform with its aspect ratio AR is equal to infinity. Its lift curve slope is. So the value for aspect ratio is equal to infinity, and we need to find the lift curve slope. So this is also easy only. We can find the lift curve slope means we need to find the A value. So lift curve slope formula is A equal to, I will be writing the formula. So A equal to A naught divided by 1 plus A naught divided by pi
So
into
is it A naught, sir?
what?
Is the value A naught? Like the answer is A naught?
No. We have some answers here.
Okay.
Some finite values here.
Okay.
So here we will be having this another one term as E, but E equal to 1. So therefore I am neglecting that term. So remaining formula is A equal to A naught divided by 1 plus A naught divided by pi AR. So the value for lift curve slope formula is A equal to A naught for elliptical platform sessions. Here the aspect ratio value they have this given data, we can get it is as infinity. So substitute the value.
So I'm getting A as A naught, sir.
So here see A naught is the lift curve slope. That is we are comparing that relation from finite wing and an elliptical wing. Okay. So for both things in a finite wing we know that A naught value is A equal to say for a finite wing, they have considered the finite wing as a naught, the lift curve slope value, and for elliptical wing they have considered as a. Okay, so for a naught the value is same value, the lift curve slope it won't change, so a naught equal to, now it is easy for you guys to solve this problem, I think so.
Sir, the answer is 2 pi.
Yes, 2 pi means we have a okay, 2 pi it is also okay. So here one thing I need to stress you, because suppose it is not a MCQ type question. We should give a value like we can write. If you are writing like this also, it is okay. Answer is correct only. Answer is 2 pi only. But we need to. It should be in. It should be as a finite number. So we need to multiply this. We need to substitute the pi value. That is 2 into pi.
6.28.
6.28, sir.
So the answer is 6 point. So answer is 6.28. Okay, correct. Everyone got this answer?
Yes, sir.
Okay. So for aspect ratio is infinity means the lift curve slope value will be equal to same 2 pi only. So the for a finite platform and for elliptical platform, the lift curve slope, if the lift curve slope for elliptical platform, if the aspect ratio is infinity means the lift curve slope value will be equal to 2 pi only. Okay, the same only. So there may be
So actually, the
twisted form.
the lift curve slope for any particular
Airfoil
airfoil
is-
section is, you told that it's said to be
Yes.
2 pi,
Yes,
sir.
yes, that is 2 pi only. That's why that is a aerofoil section, because the aerofoil section it will be, they will be asking that finite wing here. You know the aspect ratio is infinity. Aspect ratio is infinity means it is it represents the aerofoil section only.
Okay.
Okay, so therefore it is 2 pi only. Straight away you can write the answer as 2 pi.
Yes, sir.
But after substitution also we will getting the same value only. That for a substitution, for your understanding only, I asked you to solve this thing. Okay.
Okay, sir.
Okay, fine. So next thing is the compressible flows. So what is compressible flow? What is incompressible flow? Anyone?
So it's dou rho by dou t is equal to whether 0 or not. That's the matter, sir.
Yes. That is
So compressible, it's
compressible means the density is not equal to
0.
constant.
That's
Constant.
what constant.
Density changes, but for incompressible flow, the density won't change. It remains the constant. It remains constant. Okay, that is the thing. So we have splitted the compressible flows and all in the terms of Mach number. So if the Mach number is less than 0.3, it will be considered as incompressible flows. If it is greater than 0.3 and all, we will be considering that as compressible flow. So if Mach number is less than 1, the flow is called subsonic flow. Mach number less than 1 is subsonic. Mach number then greater than 1 is supersonic. Mach number equal to 1. These all things you know, but we'll be focusing on these things only in the upcoming sessions. That's why I am starting this. Equal to 1 is sonic, then Mach number from 0.8 to 1.2 is, we'll be calling it as transonic. Then Mach number greater than 5 is, we'll call it as hypersonics. So These are the different flow types that is categorized based on Mach number. So in this session, we'll be focusing on compressible flows, then shock waves, different types of shock waves, and the problems related to shock waves. Okay. So first of all, what is incompressible and compressible flow? Incompressible flow is a fluid flow in which the density remains constant. But for a compressible flow, the density varies with pressure. That is, the density is not equal to constant. Okay. Then the main important term is compressibility. Most of the questions get question also in other MCQ question also they will be asking questions from this compressibility, that is tau formula, whether it is same and all, or they will be asking that the bulk modulus. They will be giving the bulk modulus term and they will ask you to find the compressibility. Then see. So the amount by which a substance can be compressed is given by a specific property of substance called the compressibility. Or we can give another one definition for that. It is a fractional change in volume of the fluid element per unit change in pressure. So fractional change in volume of the fluid element per unit change in pressure, that is called compressibility. So the formula is for isothermal process, or straight away we will be having the formula like this: tau equal to minus 1 by v integral of into dou v by dou p. So for isothermal process, we will be putting the t here, suffix t. For isentropic process, we will be putting suffix s. So the tau value will be in terms of volume, that is 1 by v dou v by change in volume divided by change in pressure. That's volume change in volume of the fluid per unit change in pressure. Same way, in terms of density means rho equal to v, v equal to 1 by rho. So tau equal to 1 by rho d rho divided by dp. Change in density divided by change in pressure. In terms of density means the compressibility formula is d rho divided by dp. So one more thing, if the degree of compressibility of a substance is categorized by bulk modulus of elasticity. So based upon bulk modulus also, we can easily calculate the formula will be same only, because bulk stress equal to dou v by change in volume or change in pressure at the stress means force by area, and also strain change in volume divided by original volume. So by applying this, we will be getting that k equal to 1 by tau. In some books, they will be given the formulas like this: 1 by beta. So beta or tau, whatever it may be, same only. The bulk modulus, if you are given the value for bulk modulus, means we can easily calculate the tau. So k equal to 1 by tau. Actually, why this compressibility term it comes into focus by aerodynamics means first of all they have designed planes in a subsonic speed only, that is a low speed airplanes only they have designed. After that, when one day one scientist he designed the engine and it was fitted in an airplane, and while flying there are many accidents because of this compressibility issues only. But they don't know why we are getting some issues, because we know the shock formation, it is formed over the aerofoil. We know the critical aerofoil and all. Anyone please explain what is critical aerofoil or critical Mach number? Please explain what is critical Mach number. Hello.
So at any point of the airfoil where the Mach number reaches unity is called critical Mach number, sir?
Yes, at any point of the airfoil, the local Mach number reaches unity, that is m equal to 1. It becomes over the surface of the airfoil. That is called critical Mach number because of the shock formations which formed over the surface of the airfoil. See, this is the thing that this is the airfoil. Sorry, we can see this is the airfoil. So in normal aerofoils and all, if you are going in a we are approaching like the 0.8 Mach number m equal to 0.8 and all over the surface of the aerofoil. At some point, we will be getting m equal to 1. This is called critical Mach number. But in order to this will increase the drag. That is a drag divergence Mach numbers and all. Increase the drag of the aerofoil. In order to minimize the drag, what we do means we change the shape of the aerofoil in the form of in the form like this. This is called this type of aerofoils. The surface will be like a flat surface over the top surface of the aerofoil, and aerofoils will be thick. And this kind of things we will be saying it as supercritical aerofoils. While if in normal aerofoils, suppose the local point where m equal to 1 is the location is here, means in supercritical aerofoils it will be moved downwards or downstream, and the shock will be formed, or the m equal to unity, m equal to 1, it will be formed here. At this point, it will be shifted somewhat downstream. So for that purpose, if that the critical Mach number that is shifted downstream means the drag will get reduced. So this is the main thing for implementing supercritical aerofoils in business jets, and also for in transport airplanes, and also in not in fighter airplanes. Other than fighter, the business the transport airplanes and all transonic airplanes which is flying in transonic speeds will be, they are using this type of aerofoils only, supercritical type aerofoils only. See, if over the surface.
So you are saying that the separation point is being delayed, sir?
No, separation is also delayed, because if see, that's what we are going to focus on this in upcoming sessions, because beyond the shock, there will be large change in aerodynamic properties. What are the changes in aerodynamic properties that we will be seeing? See, the separations and all, when the flow is detached from the surface of the aerofoils, we will be getting the separations. And the separations also, there are a lot of that is LSB. LSB layer, one term called LSB layer. Then the inflations and all that you have studied, I think so. The point of inflation, that adverse pressure gradients, that all things you studied now. That is when the flow is get reversed. First of all, where the suppression start means if there is a point of inflation over the surface of the boundary layer, or the over surface of the airfoil and the boundary layer. If there is a point of inflation comes in focus, that is in normal. If the flow is attached over the surface of the aerofoil like this, I will be drawing. See, this is the surface of the aerofoil. If the flow is attached like this, the point of inflation will be like from inside here. If the flow is detached from the surface, the point of inflation, it moves upward and it will reach the surface of the aerofoil, because the flow is here. So while moving downstream, the inflation, it will move upward and it will come here. So if from the point of inflation only, the separation starts. That's the main thing. Then you all know that the transition region, turbulent region, laminar region and all. So after laminar region, where the flow separates is from the point of inflation. When the point of inflation comes into the focus of the boundary layer, then from there the separation starts. Okay. So before entering into these things, so
Sir, I'm having a doubt.
Yes.
Sir, if we want that the flow to be completely attached over the aerofoil, the point of inflation should be within the aerofoil throughout its chord.
Yes, throughout its chord. If the Kutta condition is satisfied, then the point of inflation is inside the aerofoil only. That is that means actually actually means, see, we are drawing the boundary layer like this. We will be drawing like this. We will be drawing like this. This you all know. But when separation starts, we will be drawing like this. So in between here, first of all, the separations, it will start from little bit. It will be like this. So sorry, little bit like this. But after when moving downstream, it will be like this. Then the separations will be in the form of like S shape. This regions, it will be like in the form of a bubble layer. That is why it is called
Turbulence.
separation. Turbulence. No, no. LSB. Separation bubbles formed downstream. Because of this only, stalling process will start. Normally for airfoils, greater than angle of attack of after 8-degree angle of attack, this point of inflation comes to focus over the surface of the aerofoil. Otherwise, it will be in the flow will be attached only. After 8-degree, we can see little bit inflation over this. Here in this point, the inflation will be here. But here the inflation, it changes to, it moves here. Subsequently, while moving downstream, it changes, it moves upward. So while the inflation moves upward, automatically adverse pressure gradient comes into picture. See, I don't know who yes, someone's voice is interrupting. Please mute your microphone, please. Okay, thank you. So while moving downstream, the point of inflation, it moves somewhat upward. So the point of inflation, when it moves upward, what will happen? The pressure, adverse pressure gradients, it will comes into picture like this. So here the pressure gradient is little bit low only. After moving downstream, you can see the pressure gradients, it will grow. So the suppression bubbles, this is the aerofoil, top surface of the aerofoil. When the angle of attack is 0-degree, the flow will be in the form of attached only, fully attached. When it is go beyond 8-degree, if you are getting 8-degree, what will happen? From the trailing edge region, somewhere the inflation starts or the separation starts. The flow separate like this. If you are changing the angle beyond 12-degree, means it will this boundary layer, what will happen? It will move somewhat forward. So the separation, it starts from here. The separation will move beyond. So while designing an aerofoil, or see so many concepts there for designing an aerofoil, or giving different types of aerofoils, different types of things. So why we are stressing, or we are focusing on the researchers, why they are focusing on this type of things means, main thing is to, at high angle of attack, we will be having the stalling region and all. So after maximum CL, we will be getting this stalling that wing will get stalled. So main focus is to reduce the stall. If you want to reduce the, if see here, I shown the two diagrams. This is one for angle of attack 8-degree, and another one is for angle of attack 12-degree. So if the separation moves forward, what will happen? The stall is increased. But our the researchers, the main focus of the researchers are, they want to design an aerofoil. That aerofoil, while increasing the angle of attack, the stall region, that means the separation region, it should move further downstream only. It should not move forward. Suppose I'm designing say it is a NACA 441 aerofoil that will be stalled at 12-degree. Suppose I am designing some aerofoil with a morphing concept or some other concepts, and that aerofoil, what will happen? The separation, it moves beyond. That means when I am increasing the angle of attack to 15-degree only, I am getting the separation which I got in NACA 4412 aerofoil. So there is a difference now. So for if the angle of attack is in 12 degree for a newly designed aerofoil, the separation is here. But for NACA 441 aerofoil, the separation is somewhat before. So the angle and the aerofoil stalls at a smaller angle of attack, not at a higher angle of attack. But for a newly designed aerofoil, it is stalling at some later angle of attack. That is at a 15 degree angle of attack. Now you guys understand what is the difference and why we are researchers are mainly focusing on these things and mainly focusing on the boundary layer concept. Do you understand?
Yes, sir.
Okay, super. So if you are designing an aerofoil, you should design an aerofoil with that should stall at higher angle of attack. That should not stall at lower angle or some smaller angle of attacks. Okay, that was the main thing.
So can
okay.
you please explain about the techniques that are used for delay in the flow separation process of an
Yes,
airfoil?
delaying the flow separation process. See, some they will be changing the camber and also see they will be changing the camber. They will be changing the thickness also, and also some they will pass a jet here. So they will pass a jet of air over the surface of the airfoil where the stall occurs. So what will happen is where the separation start, it will move somewhat backward. So these are the things. Some morphing concept they will use. So they will be using some morphing concepts or some other techniques for delaying this stall and all. Okay.
So can the roughness of a surface can be increased?
No, roughness increase means automatically drag will increase now. You should not increase the roughness and all.
Like the flow must be attached to the surface for a longer period of time, sir.
Yes, the flow should be attached for the longer period of time, but see if the we should not one more thing we should focus, because here lift is also concerned and also drag is also concerned. We should get we need maximum L by D ratio. Okay, the L by D ratio should be maximum. If see, shear stress is if viscous the roughness is higher means automatically the shear stress is bigger. So shear stress come into focus. And if shear stress is higher means what will happen? Automatically drag. There won't be any lift. The lift will be much lesser compared to the normal. That's why they are smoothing the aerofoil. That you have done experiments for rough cylinder and smooth cylinder aerofoils now. Smooth cylinder
Yes.
experiments. Why they are giving a smooth cylinder? This is the difference. We should not give that if there is a roughness means automatically drag comes into picture. Okay. Okay, fine. So now shall we move on to the topics, or shall we stop here? Okay, it is so I will be telling some small basic concepts for this thermodynamic relations and all. So we all know that equation of state, that is PV equal to mRT. So R else P equal to rho into R into T. Suppose the gases are we know the from first law. What is first law? Anyone? Please, first law of thermodynamics.
Energy neither be created nor be destroyed, sir.
What? I couldn't understand.
Energy neither be created nor be destroyed, but it converts from one form to another form.
Yes, it converts from one form to
Another form.
okay. So what is the formula for the first law? What is the formula for first law of thermodynamics?
Sir, del U is equal to Q minus W. Change in internal energy is equal to Q minus heat added minus work done.
Okay. So the work heat is converted into work. Main thing is the heat is converted into work. Okay. So del E equal to Q minus W. That's in the formula here also. I'm giving the formula. Del equal to here Q del Q. There is a we will be writing like this. Del Q equal to or Q plus W equal to del U. That's why here this. So how work is transfer? Sorry, heat is transformed into work that we will be seeing in thermodynamics we have seen. But we won't need that things here. Just we need some small internal energy formulas, then work formula, and also from how temperature the Q formula. That only we need here. So here from the first law of thermodynamics, T into ds equal to d plus p into dv. P into dv, that is work. Then also another one formula, internal energy h equal to u plus pv. So the formula is T into ds equal to dh minus v into dp. So for calorically perfect gas, we have another one formula, that is u equal to mcv into dt, and h equal to, that is del h equal to mcp into dt. For unit mass, here calorically perfect gas, that is for unit mass, we will be giving like the formula like E equal to cv into dt, h equal to cp into dt. So we know the formula for a gas constant, R equal to cp minus cv. Do you know how this cp equal to this formula come from this come? We know R equal to cp minus cv, and also gamma equal to ratio of specific heats, gamma equal to cp divided by cv. So cp by cv equal to R. From this R equal to, so R equal to taking that cv outside, so cp by cv minus 1. So R by cv equal to gamma minus 1, because cp by cv equal to gamma. So from that, here I'll be writing. From that, cv equal to R divided by gamma minus 1. We know R equal to cp minus cv. So substitute the value for cv. Therefore R equal to cp minus R divided by gamma minus 1. So therefore R plus R divided by divided by gamma minus 1 equal to cp. So by solving this, gamma R minus minus R plus R, so R get cancelled. Therefore the remaining terms will be gamma R divided by gamma minus 1. So the cp equal to gamma R divided by gamma minus 1. Then cv equal to R, same way substitute substitute the cp value in here, so we get the cv value here and also cp value here. So cv equal to R divided by gamma minus 1, and cp equal to R divided by gamma R divided by gamma minus 1. These formulas we need for our upcoming sessions, that is for in a normal shock and all the problems we need in this type of formulas. So just note these formulas.
Excuse me, sir.
Yes.
So has the previous class notes been uploaded in the website, sir?
Yes, that was uploaded. I've given the notes. I think it is uploaded. After this class also, I will upload this notes also. You can, so that you can easily access this notes. Okay.
Okay.
Okay. So we will be winding up the session. We'll be having our next session in the evening. Okay. Huh?
Sure, sir. Thank you.
Okay. Okay.
Thank you,
Thank
sir.
you. Thank you. Thank you so much.